Did you know that flipping the bits of a number, literally reversing them, is a favorite Phong interview question? Reverse bits is a classic pattern mastery 100 problem that seems simple, but it reveals who really understands how data is stored and manipulated at the lowest level. Master this, and you'll unlock a new level of confidence for bitwise questions, data encoding, and optimization. Let's break it down. Given a 32-bit unsigned integer, reverse its bits and return the resulting integer. For example, if the input is 100 in binary, you need to flip the bit so it becomes 001. Let's assess our approach. The brute force way is actually perfect here. Loop through all 32 bits, and for each one, shift the answer left, add the current bit from n, and shift n right to process the next bit. This runs in 01 time, since 32 is constant, and 01 space. Here's the structure. Initialize result to 0, for 32 times, or as many as the number's bit length. Shift result left by 1, to make space for the next bit. Add the least significant bit of n to result or equals n and 1. Shift n right by 1 to process the next bit. When done, return result. Let's try to implement it using solution 1. Here we're defining a function called reverse bits that takes in a number n. The goal is to reverse its bits, basically, flip the binary digits so the left side becomes the right side and vice versa. We create a variable named res and start it at 0. This will be our builder number. We'll construct the reversed bit result one bit at a time. Now we loop exactly 32 times, because we're working with a 32-bit number. Time complexity note: this is always 32 steps no matter what n is, so it's 01, constant time. This line does the main work in 2 moves. First, res1, shifts res left by 1 bit, that's like making room for a new bit on the right side. Second, n and 1, grabs the last bit of n, it's either 0 or 1. Then we combine them with vertical bar, which means, stick that grabbed bit into the new space. Think of it like this: we're building the reversed number by repeatedly taking the rightmost bit from n and appending it onto the right side of res. Now we shift n to the right by 1 bit using which is a 0 fill right shift. That means we drop the bit we just used, and slide everything over, filling the left side with zeros. It's like moving to the next bit to read. This closes the loop. After 32 rounds, we've taken all 32 bits from n, in order from right to left, and rebuilt them into res in reverse order. This returns the result, but with a small JavaScript detail: 0 forces the number to be treated as an unsigned 32-bit integer. That keeps it from turning into a negative number due to how JavaScript handles bit operations internally. And that finishes the function. And that's how this algorithm works. It first sets up a result bucket starting at 0, then it repeats 32 times, shifting the result to make space, grabbing the last bit of the input and attaching it, while shifting the input right to move through all bits. Efficient, simple, and elegant. Let's test our function using this input. N equals 43,261,596. This number represents a 32-bit unsigned integer, and our job is to reverse its bits, meaning the leftmost bit becomes the rightmost, and vice versa. Here's why the solution works. We build a new number res 1 bit at a time, on each of the 32 steps. We take the last bit of n using n and 1. Shift res left to make space, then drop that bit into res. Then we shift n right to move the next bit into position. So after 32 iterations, we've taken n from right to left and reconstructed res from left to right, which is exactly a bit reversal. For this specific input, reversing the 32-bit pattern of 43,261,596 produces 964,176,192, which is the known correct reversed value. And that's exactly what our program outputs: 964,176,192. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully reverses all 32 bits of the input integer using consistent bit extraction and shifting, efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called reverse bits that takes a number n and returns a new number where the 32 bits are reversed. Think of it like taking a 32-character binary string and flipping it backwards. Time complexity: 01 here because we always deal with a fixed 32-bit length. This line turns n into a clean 32-bit binary string. N0 forces n to be treated as an unsigned 32-bit number, basically keep the bits as is, no negative confusion. Dot to string 2 converts it into a binary string, like 1011 instead of a decimal number. Dot pad start 32, 0, adds leading zeros so the string is exactly 32 characters long. So even if the binary form is short, we make it a full 32-bit representation. Now we reverse that binary string. Split breaks the string into an array of single characters, like 1, 0, 1, 1. Reverse flips the array backward. Join stitches it back into one string. So R becomes the reversed 32-bit binary string, like reading the bits from right to left instead of left to right. Finally, we convert the reversed binary string back into a number. Parseint R, 2, reads the string R as a base 2, binary, number. 0 again forces the result to be treated as an unsigned 32-bit integer, so we return the correct non-negative value. And this last line closes the function. Done. And that's how this algorithm works. It first converts the number into a padded 32-bit binary string, then reverses that string, and finally converts it back into an unsigned integer. Efficient, simple, and elegant. Let's test our function using this input. N equals 2,147,483,644. This number represents a 32-bit unsigned integer, and our goal is to reverse all 32 bits of its binary representation. Here's why the solution works. We convert the number into a 32-bit binary string, reverse that string, then convert it back into an integer. So we're literally flipping the bit order from left to right. For example, first, N0 ensures we treat N as an unsigned 32-bit value. Then we do to string 2 to get its binary form, and pad start 32, 0, to make sure it's exactly 32 bits long. Next, we reverse the entire string with split reverse join. Finally, parseint R, 2, converts that reversed binary back into a number, and 0 keeps it unsigned. So for 2,147,483,644, reversing its 32-bit pattern produces 1,073,741,822, which is exactly what we expect after the flip. And that's exactly what our program outputs, 1,073,741,822. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully reverses the full 32-bit binary representation of the input integer by converting, reversing, and converting back, efficient, accurate, and reliable. Alright, let's quickly recap what we learned about reversing bits in a 32-bit unsigned integer. Breakdown recap. We started by understanding that the task is to flip the order of bits, turning the least significant bit into the most significant, and vice versa. Conceptually, it's like mirroring the binary pattern of the number. Assess recap. We realized that a simple loop-based approach works best here. There's no need for optimization tricks. Iterating through all 32 bits is already efficient since the bit count never changes. Structure recap. We built our logic step by step. Initialize a result, shift it left each time to make space, take the current bit from the original number, and move to the next bit by shifting right. Implement recap. We then implemented this logic directly in LeetCode, and the code ran smoothly without any syntax or logical issues. Check recap. Finally, we verified our result using LeetCode's test cases, confirming that our function correctly reversed the bits every single time. The key takeaway here is that sometimes the most direct approach, like looping through each bit, can be both clean and optimal. Bit manipulation problems often reward clarity over complexity.